Hi guys, welcome to Tronic Synergy, where we do fun stuff all day, all time. And today we have done another pretty simple circuit. This is a full adder circuit. Remember last time we did a half adder circuit on our previous session. Now today we have done a full adder circuit, and this is a schematic diagram of our full adder circuit. We'll go more into details when I'm going to show you individual parts and how I've connected them. So our circuit is right here and it is on. So our full adder circuit, our output should look like that. So we have three inputs. We have A, B and carry in, and our output will be in this form. Then it will be having a carry out section right there. So we can go right away and start. I can demonstrate how it works. So it's on already. So when all inputs are 0, we get a 0 output. Output is green LED. Then our carry out is orange LED. So we get a 0 on all sides. Then when we have a 1 right there at the carry in, we have a 1 output, but we don't have a carry out signal. So yes, so we continue. Then we put this off. Then our B, sorry, let me try to make this well, yes, like that. So B, we put it on. Then B, we have a 1 output and 0 carry out. Then our next one is when B and carry in are on. So I'm going to light this on. Then we get a 0 output but with a carry out. 0 output but with our carry out. Then our next one, A is on but B and carry in are 0. So we put this 0. Then we put A on. Then when A is on, we get a 1 output and a 0 carry out. Then the next one, A and carry in are on, so I put carry in on. Then we get a 0 carry 1 right there, so a 0 output and a carry. Then our next one is A and B, so we put carry in off, then we put on A and B. We get a 0 output but a 1 carry out signal. Then our last, when all inputs are 1, so I put this on. Then we get a 1 output and a 1 carry out, and that's what we are going to do today. Please enjoy. So welcome back guys. So today we are going to do a full adder circuit, and remember previously we have done a video about a half adder circuit. So our half adder circuit had only 2 inputs and it gave a 1 output. So the difference between that and this can handle 3 inputs, and it can consider the output of the previous summation to the next in order to give you one output of the combined operation. So this is more powerful, if you compare this to the other half adder. This is more powerful, and it's pretty much simple, you can see. So just like the other one, I'm using N555s as automatic switches, which are very easy. I'm also going to be pressing these buttons. I just like the switching of these because I don't have that mechanical switch that you switch on and off directly. So I'm going to use N555s instead in bistable mode. You can use the switches that you have. If you have a big size breadboard, maybe you can use even some big switches, but my breadboard is just a normal size, so I'm going to use these NE555 switches. They're in bistable mode. I'd done some video back in some few months ago about how to connect an NE555 in bistable mode. I'll put it in the description so you can go and check how to connect that circuit. So this is pretty much the same. So bistable means it has only two inputs. It's either on or off, and you're the one to control whether you want it to be on or off. So the on will be taken as a 1 output, as a 1 input in this digital circuit, and off will be taken as a 0 input in this digital circuit. So our first NE555 right there and our second NE555 gives the A and B input to the digital circuit, to the logic gates. Then our third NE555, which we have added, this was not initially there, as you can remember in our previous half adder circuit. We have added this, and it's going to give an output of a carry in. So our carry in will be another input of our logic gates in our logic gate circuit, in order to give a three addition of three binary in order to get one output. So A and B enters the first XOR gate. Then our output of our first XOR gate enters the next input, enters the next OR gate as an input. The other input of the XOR gate comes in from the carry in, which is our third NE555. Then the output of that second XOR gate gives the summation. So this gives the summation of the three inputs, A, B, and carry in. Then from there we have two AND gates. So our first AND gate gets its input from the output of the first XOR gate. Then the other one it gets from the carry in, and it goes straight to an input of our OR gate, which is going to be giving us the carry out. And our next input comes from input of our OR gate comes from an AND gate, which has inputs A and B. So this gives the output of that AND gate enters to be the second input of the OR gate, the last OR gate. So this is the one that is the final one, and it gives the carry out signal. So this is the carry out of the considering all the three inputs, A, B, and carry in. So it's pretty much simple. It's just connect. If you look at it correctly, just interconnecting the half gates together in order to get a one full adder circuit right there. So you can check the schematic once again, and you can screenshot it, and you can maybe start building your circuit at home. So I'm using a 5-volt power supply. You can use any from 3 volts and to 9 volts. Please check the ratings of the components which you're going to use in order to avoid overpowering them. So yes, so my circuit is right here. Don't worry, it looks pretty much it looks like a mess because the interconnections, because I don't have the XOR gate, so I'm pretty much making it using the AND gates and the OR gates right there in order to make the XOR gate, so, and the NOT gate. So if I add the XOR gates, it will be pretty much easy, but because I don't have, I have to make them directly. Also, I realized that my AND gate integrated circuit has only 4 AND gates, and I already used all of them while making these 2 XOR gates. So I needed one more AND gate, and I got it from and I made it right here. You can see it in this end with these 2 transistors. So you also need to check how to make. You also can make these logic gates using transistors as an alternative if you don't have the AND gate themselves as integrated circuits. So this is another AND gate that I made using transistors because I realized that I didn't have enough AND gates to build my circuit. So that's pretty much it. Our 3 and 5s are right there, and their push buttons are right there for on and off, on and off, on and off. Then the inputs enter the logic gates, which I've explained there, and the output are right there. So the green LED shows the summation, and the orange LED in the far end shows the carry out signal of our circuit. So yes, so we are going to power this thing, and we are going to check how it performs. So I've powered it on. Don't know why this is on. Should not be on. I don't know why it's on. Okay, fine. So I have my truth table here, so we are going to follow this, and then we'll see if we get what we have there. So if I put all of them on, I should get a 1 output and a 1 carry out. So I put them on, all of them. Yes, all the inputs A, B, and carry in are on, so I get a 1 output and a carry out. That's correct. So the next one, A and B are on, but carry in is off. So A and B are on, but this is off, so I put it off. So I get a 0 output, green LED is off, but a 1 carry out. So that right there. Yes. Now we can, why is this off? Is this off or on? Oh boy. Let me just try to power this thing again. It's not. Let's start all over again, because this thing is not. Oh boy. Okay, let's start it over again. I don't know why these jumpers are not working properly. Okay, let's start it over again. So when all inputs are 1, we get a 1 output and a 1 carry out. So the next one, A and B are on, but carry in is off, so I put it off, and we get a 0 and a 1 carry out, 0 and a 1 carry out. Then our next one, A is on, but B is off, but and carry in is on, so I put this off, I put this on. So A and carry in are on, we get a 0 output, yes, green LED is off, but carry out is 1. Yes. Then the next one, A is the one which is on, but all the others are off, so I put this off. So A is the one which is on, so we get a 1 output and a 0 carry out. 1 output and a 0 carry out. Yes. Our next one, A is off, B and carry in are on. A I'm going to put it off, so I put it off. Then B and carry in are on. B and carry in are on. So yes, so we get a 0 output and a 1 carry out. 0 output and a 1 carry out. Our next one, B is the one which is on. B is the one which is on. So we put this off. B is the one which is on. So we get a 1 output and a 0 carry out. So pretty much, so basically what the circuit does is that when 2 inputs are on, we get a 0 output and a carry 1. But when 1 output is on, we get a 1 output, but carry out is off. So when 2 inputs are on, we get a 0 output, but a 1 carry out. So if I put this on, we get a 0 output, but a 1 carry out. But when only 1 is on, we get a 1 output, but a 0 carry out. if let's say is this 0 0 0 and 0, if all of them are 0, then we expect the output to be 0 and the carry out to be 0. So that's basically what the circuit does, and that's how a full adder circuit functions. So I hope you have learned, and I hope you are going to try to build this. Mine looks a bit messy because I had explained I don't have an XOR gate integrated circuit, so I had to make them using the AND gates. That's why I've interconnected them very much. So you can try this at home. Try to look for XOR gates rather than doing what I've done, because this is just a mess, and you can connect them wrongly using this. So try to find an XOR gate and make your circuit quite clear in order to get the concept well. So thank you very much guys for watching. Please subscribe to Tronic Synergy, where we do fun stuff all day, all time. Hope to see you next time. Goodbye.